Okay, just to introduce myself a little bit. I'm a Java champion. I have one of the most answers in the world on Stack Overflow for Java in the JVM. I was the first to get a gold badge holder in memory, file I/O, and concurrency in any language on Stack Overflow. So my most recent article got about 17,000 views in a couple of days. And some of the content here is based on that article and also previous articles. What else? Okay. So as an organization, a lot of our clients are in banking, but a lot of our open source software is used all over the world. So we get about 7,000 downloads a month from different IP addresses for our individual open source software. And overall, it's about 4 million a month across all of our products. But in terms of commercially, 80% of our revenue comes from tier 1 banks. One of them you probably know is UOB, for example. It's a local bank. So today I'm talking about a number of topics that really got my interest and attention recently. Something I see again and again between different clients. And one of the things that frustrates me the most is the level of what's called accidental complexity. And accidental complexity is where your application is spending a lot of time doing things that are not actually business requirements or even requirements from IT either. Certainly we've seen cases, even quite recently, where it's 2 or even 3 orders of magnitude of the time spent is not actually fulfilling the business need, but is actually just because of the tools or the strategy they've used or the approach they've taken. So I look at a specific example that's covered in one of my articles. Another one, the one that got the most interest, is about showing that allocations don't scale. So as you have more and more threads creating objects, you reach a saturation point such that the system cannot allocate more objects just by having more threads. And this is shared globally. So if you've got multiple virtual machines, then it's not partitioned, it's not a shared resource. One 4 CPU virtual machine is enough to saturate an entire server, almost regardless of how many CPUs it has. So it is something that you do need to pay more attention to than you probably may have done in the past. Then I look at both behavior-driven development and data-driven tests and why they are relevant to low latency systems in particular, or also make systems more maintainable and improves the velocity of development. And then I could go into some coding examples. So all of these have got benchmarks and code. The articles have links to them from my blog, but I'll show you some of the code here today as well to give you an idea of what does this look like. And if we have time, we'll get into some durability guarantees and why they're important to look at. In particular, if you have a database in your critical path, that can be such a dominant feature in your latency and determining the throughput that nothing else you do probably matters too much. So I'll look at some alternative strategies for not using the database in your critical path. So what we want to do is we want to focus on clear requirements that either come from the business or from IT or we've established ourselves, and stick to those requirements and say, well, what's the most effective way of delivering on them, rather than, well, what's something that works. That discrepancy can be enormous. And in particular, so many projects we see, particularly in banking, but I guess also in other industries, where the velocity of development declines quite rapidly to the point where it's very hard to change anything compared to when the project started. And what we want to do is avoid that happening. So if we from the start make sure that the velocity of development can be maintained, then you have a much more maintainable project. You can keep delivering to the market new changes all the time, and your project won't essentially be put it to one side and say, well, we can't develop this anymore, it's just too hard, let's start again. So accidental complexity is where your application is spending time or resources on things that aren't actually a requirement. And in particular, this can also be when developers are spending time on things which are not, the business doesn't actually require. And that's often down to not having clear specifications, where the business either can't tell you or hasn't tell you, or it's not being communicated, or maybe it's being communicated to someone else but not necessarily to you. And so going back and focusing on what does the business actually need, what does IT actually need from you, because the business won't specify all the requirements. Really focusing on that, you can cut down the amount of work your team has to do, cut down the amount of work the application has to do, and deliver much faster. Whereas, essential complexity is what you actually need to do. What can't be taken away. Maybe you can do it a little bit differently, but fundamentally your application will need to do that because that actually meets a requirement. Now, how is it possible that you could get an accidental complexity that large, right? Like 2 or 3 orders of magnitude. One of the causes of this is your application will have multiple levels of abstraction, right? And even in our case, we try and cut down the number of levels of abstraction, but still there are multiple levels of abstraction. Each level of abstraction will often do a bit more, perhaps even a lot more than is really required by your application at that time. And by the time you've run this through multiple levels, each one of them adding a percentage, they multiply together until eventually you can get 10 times, 100 times, and in some cases even 1,000 times more effort going into it than what is actually strictly required. Let's take a concrete example, right? So I'm just throwing numbers out to you at this point. But so in this case, this is a benchmark where a message is sent via a queue to a service or a microservice, and that microservice sends back a reply, which is in fact the same message, back again via another queue, and they're picked up by the client. Now look at the round trip latency. Now Kafka is described as a low latency product. It is lower latency than a lot of alternatives. It's not a bad implementation. That's not what I'm suggesting here. And in fact, when I benchmarked it, I was able to get latencies around half what a lot of the vendors that support it publish. So I think they can actually do better if they improve their benchmarks. They would get better numbers. But yeah, so I can still get good results with Kafka. But doing exactly the same thing with a Chronicle queue, and this is the open source version, the latency difference is around about a factor of 750 to do the same thing, right? Send a message, serialize it, deserialize it, persist it. This is all on one machine, so it's a very simple configuration, simplest possible configuration. So network traffic isn't really part of the equation here. We're just looking at the overhead of passing a message to a service via a queue and getting it back via a queue. So this difference is so large that it can be difficult to even conceptualize. And part of the reason why it's not such an obvious problem is that in this benchmark, Kafka was getting, on the 99th percentile, which is the worst one in 100, Kafka was getting about 2.6 milliseconds. Now in their own benchmarks, they were getting about 5 milliseconds. So I thought it was being reasonably fair to them by actually getting 2.6 milliseconds. So how far can a signal go in 2.6 milliseconds? So instead of representing it in terms of an amount of time you can't even imagine, you can't see 2.6 milliseconds, let's turn it into a distance. Like how far can the signal go in that time? So that's something you could think of considering as well, is that if you're trying to convince someone this is a long time, but it's still, you're working on a system where actually this is shorter than you can see, how do you convey that another way? And so 2.6 milliseconds is about the time it takes to send a signal from Singapore to well past Kuala Lumpur. So that's quite a long distance that a signal can go in that time. Whereas with Chronicle, the amount of time is it's around 30 microseconds, and the distance that a signal can go there is from boat key to Clark key. So you can see that's a much shorter distance. And like I said, it's doing the same, it's meeting the same requirement, right? And it's even difficult to chart. So this is a log chart where on the vertical axis, you've got powers of 10. It's the only way to get them both on the chart at the same time because the difference is enormous. As you can see, like on the 90th percentile, you're getting around 3 microseconds here. Up there, you're getting about 2,396 microseconds. And that's at a lower throughput. If you increase the throughput to similar to what I was doing for Chronicle, it goes up by another factor of 10 or even 100. So it's quite a huge discrepancy. And again, like I said, this is just doing the same work. And I'm not necessarily talking about messaging here. We've seen other examples where doing the same function but in a different manner can cut down by 1, 2, or even 3 orders of magnitude. So what's the benefit of doing this, right? So what? I mean, so what? How does this help me as a developer, right? Because the business has said, oh, they're happy with a few milliseconds, and actually, there might be. What is the benefit to having it less than a few milliseconds, right? Because you're meeting the business requirement. Well, in this case, what happens? In this, this is how long it takes to build our one of our key pieces of software. It's the EFX trading system. And it's time to compile all the code, run all the tests. Now, each of those tests starts up a service and shuts it down. So instead, we're not timing how long to send a message, just how long to start up a service, test it, and shut it down again, and check that it's doing the right thing. So in this case, it's doing 466 tests. It's doing the Java doc, building it, creating the jar and everything. Even though, end-to-end, it takes 77 seconds to do the whole lot on my development machine. So this is just on one machine, tests the whole thing, including some integration tests. And one of the key points is this is only if you're doing everything, right? Obviously, if you're just doing some point tests with one microservice for a key piece of functionality, you're talking about less than a second. And the benefit to you is that that means your whole development lifecycle is much, much shorter because you can run through hundreds or even 1,000 tests in a very short time frame because everything is running very efficiently and very fast, and it can run on your local machine without having to go, push the software up to some server, wait for it to upgrade, and then maybe you run into some issue because you're using a server that someone else is using, and you've got some sort of conflict going on. None of that's happening here because your system is efficient and fast enough that it can just run on a single machine. So that's a benefit to you, right? It helps you be more productive, not just it runs faster in production. Yes, there you go, that'll do. So moving on to the next topic. So this is about, this is something I've seen again and again, not so much in our space because in low latency space you tend not to create a lot of objects, a lot of it for this reason. So there is a perception that creating objects is cheap. And the truth is, if you've got one thread and you run a JMH test and you're creating objects, they are cheap. But in production, you're not running one thread. You're not just using one core. You want to use all the cores. And if you want to use all the cores, they're all going through a small number, maybe only one L3 cache. They're all sharing that L3 cache, and that's a contended resource. So really what you want to do is each one of your threads, you want it to fit comfortably in your L1 and L2 caches. And even though you can now get gigabytes and even terabytes of memory in a server, your L2 cache is 256K. That's for code and data. So the last thing you want to be doing is creating memory pressure by literally filling it with garbage, right, as fast as you can. So an example I've got here, the time it spends pausing is, compared to the time it spends doing allocations, is a factor of 80. So the cost of allocating is 80 times higher than the cost of actually pausing itself. So tuning the pause reduces jitter, and that shows up in your metrics. It's something you record, but the cost of allocating can be much, much higher. And even a small number of allocations can make a big difference, at least to a benchmark. And it won't necessarily affect your application, but what it will do is it will affect your ability to handle high load or bursts of activity. So this is, again, the sources in my blog for this, but if you've got just two, in this case, I've got two threads creating small objects of 44 bytes as fast as possible. How fast can two threads create 44-byte objects? And you get a pretty good rate of 126 million a second. That's a pretty big number. And the allocation time is very low, 15 nanoseconds. And generally, if it's just 15 nanoseconds, you wouldn't need to worry about it, right? However, by the time you got to just 4 threads, and this is a machine that 32 logical threads, by the time you got to 4 threads, it's starting to tick up, right? It's not getting twice the throughput anymore. And in fact, the average latency has gone up by 20%. It's now 18 nanoseconds. But still, 18 nanoseconds is nothing to worry about. It's not going to make a big difference. However, you see that actually as you add more threads, the throughput doesn't go up, really. The 6 seems to be slightly better, but essentially 32, even across 2 JVMs, you get the same allocation rate as you did with 4 threads. So all those additional threads weren't really being utilized, or they weren't adding any benefit, because somewhat unrealistically, I'm creating objects as fast as I can. And importantly, in this case, the average latency has gone up from 15 nanoseconds to 150 nanoseconds. It's taking 10 times longer to do the same thing because I've saturated the box. And it may not be you saturating the box. It could be another virtual CPU running on the same physical machine, saturating the L3 cache of the memory bus is actually the one that's causing the problem here. So if we move on. So I've got a slightly more realistic test where we were sending events over network connections over TCP. Again, it's all on one machine to keep it simple. It's going over loopback. But in this case, I'm sending events as fast as possible over loopback. Similar to the previous scenario, I'm sending an event to an echo service, and its only job is to send that event back again, right? Now, to keep things efficient, because we're in a low latency space, we're not creating any objects to do this. All the serialization, deserialization, the lookup, the method calls, none of that, and the proxies, none of them are creating any objects whatsoever. But then you might say, well, why do that? Why go to all that effort of creating no objects? What difference would just one object make, right? So you've got a lot of applications out there that if you told them to handle a whole request, you can only create one object. They'd probably think you're crazy, right? But even one object can make a difference. So in the middle chart, I'm looking at how many events per second can this system process if it's not creating any objects whatsoever. And I looked at different JVMs, different GCs and parameters. And the GC doesn't matter too much because the bottleneck here is on the left-hand side is the ability for the kernel to basically push data around over loopback. And the average latencies are very low, but you can see that they're so low that our 150 nanoseconds, although in this benchmark it's more like 170 nanoseconds, really makes a big difference, right? So in this case, what the benchmark does is if you run it in a certain mode, it will create one object for every event instead of creating no objects for every event. And that one object for every event has reduced my throughput by 25% already. That's a 44-byte object. Not a big one, really. So it's just that one object has really cut down my throughput. You still get very good throughputs, but obviously as you add more and more objects, it's just going to go down further and further in terms of what kind of throughput my system can sustain. One thing that's interesting here is there is an uptick from Java 8 to Java 11, but otherwise the version doesn't seem to make, for this use case at least, didn't really make a lot of difference. Java 17 happened to get the slightly better result. I'm not sure that if you had a different use case that would also happen, but anyway. So we go on. So what, I mean, without going to all of this work and trying to benchmark, is there something simple I can do to work out whether it's likely to be a problem or not? And in fact, the peak throughput at which, allocation rate at which your system saturates doesn't actually vary that much between servers, to be honest. So my high-end laptop, which has a battery life of an hour and something, but it goes very fast. It peaks out at about 8 gigabytes a second. A typical server will peak at about 10 gigabytes a second, which is a nice round number. And the Ryzen I was testing on before was peaking at only about 12 gigabytes a second. And I tried this on a number of different machines, and actually the variation between them really isn't that much. And a figure that Cliff Click quoted for a very similar point is that he quoted around 10 gigabytes as well as a good rule of thumb. So from your perspective, all you need to do is look at all the allocations of all the JVMs on your machine, total them up, and as a percentage of 10 gigabytes, that's how much of the time the system is spending allocating objects as a proportion of the time it's doing. So if it's creating at 1 gigabyte a second total, then roughly 10% of your CPU that it's being used goes towards allocating, which is quite high, really. And it's much higher than your GC time, probably. You might find that if you added up the GC time, so in the benchmark previously, it slowed down the throughput by 25%, but the amount of time spent in GC was 0.3%. It's very low, very efficient. You'd look at that 0.3% and say, well, allocations aren't a problem for me. Garbage isn't a problem for me, because it's only 0.3%. It's not making any difference. But actually, that's not the biggest problem. The biggest problem is the fact that you're creating memory pressure and then hitting a contended resource. So yeah, my earlier point that actually, on some systems, actually 2 CPUs is enough to saturate the machine. But on a good server, even 4 is enough to saturate it. And adding more NUMA regions and more sockets doesn't necessarily help very much. I mean, it will help, but it doesn't help. It doesn't scale, right? You have 2 sockets instead of 1. The test I did was about 25% more throughput could be achieved with 2 than could be achieved with 1. So moving on to the next topic. So behavior-driven development is one of the best practice techniques for ensuring that you are extracting requirements from the business that are clear and something you're doing upfront, and making sure that before you even start, ideally, you have at least some high-level requirements that they're looking for. And this is a methodology for doing this. Now, this isn't just an exercise for the business. This actually will help you in writing low latency or efficient software, because what it will do is allow you to focus on, well, what are the things that you actually need to do, like end to end, not all the things going on in between. I don't know how many times people have told me that it was a requirement to do something that I know for a fact if they tried to explain it to their business what they're doing, they would have no idea what they're doing or why, right? You think about, well, you think this is a requirement, go and ask the business if they even understand what you're doing, let alone, is that something they would come to you and say, this field should be an integer and not a long, right? And then you'd have to explain, well, what is the difference and why do I care and how much money will that make me, right? And you go, you know. So this will help you focus at least on the requirements they can give you. That doesn't mean all requirements come from the business. In reality, IT will have their own requirements. You will know from experience there are things they are going to need which they don't even know they need yet. So some of the requirements will come from your own experience or your team or your security team, for example. They will have their own requirements, which is just the way they do things. Don't necessarily want to question it, just say, all right, that's what they're looking for, that's what we would deliver. But once you've even got all of those, you find that focusing on just those things and not getting too much into the detail too early can help you deliver just the minimum that system needs to do. So, the overall phase here is that you start with some way of detailing at a high level the requirements. You create scenarios that fail, so this is test-driven development, and then you create an implementation that fixes that. And this isn't always the approach you need to take, but vast majority, this isn't done enough in so many projects. And then you have a passing scenario, and one of the key steps here is refactoring. So that's about reducing technical debt. Reducing technical debt might not seem important to the business, and this is one of the things that you might need to explain to them, is that reducing technical debt will allow you to help maintain velocity. As the product matures, as it gets more complicated, it will become progressively harder and harder to maintain if you're not paying off this technical debt, reducing all of the issues, the things that, okay, yes, it works, but it does it in such a horrible way that it's going to be really hard to maintain later. So you want to have at least some of the time and effort spent making sure that the code is clean, the implementations are clean, that it all makes sense, that's not just lots of things bolted together, and that will help them in the long run. Particularly if you're a developer and you get it to production, it's all that a lot of successful projects will cost 3 times as much to run in their life than they did to create in the first place. So making it maintainable helps reduce that long-term cost. So one of the benefits of behavior-driven development is, as I said, you can focus on people who have the domain knowledge, either in the business or the IT side, and they can help you give the requirements. The problem is that they're not always accessible, and sometimes when you start getting into the minutiae and the real detail that you need to write a real program, they're not always interested or have the time to go through it in absolutely every piece of detail. So rough rule of thumb is that, say for a large project, you want to be able to have about 1,000 tests or 1,000 different scenarios or whatever. In general, the business will be able to give you like 10 off the top of their head before we've even started, right? Just in the first conversation, it will just come out. These are 10 things, top 10 things I need, right? But then over time, you may extract out more and more details and feedback, but you might only get to about 100, right? But then you've got this gap, right? There's still an enormous gap between what they can tell you and what you will probably need to really nail down the system and make it maintainable. Now, what you can also do is if you've got domain expertise and you've got requirements from IT, you can go through the same exercise. You will know 10 things off the top of your head, like DR or monitorability, all these things that they may take for granted that are just there. You will probably go through a similar exercise. There'll be 10 things off the top of your head, and over time you'll get about another 100 things that you know need doing. They don't need to tell you to do that, but there's still an enormous gap, and we'll get onto how you can bridge that. One way you can bridge that gap. So because we're dealing with real-time, in our case real-time, low latency, we model all of our key systems on event-driven architecture, which is events in and events out. And in between you have a function. That function is entirely dependent on all the events it's ever seen. And that way it's completely deterministic. That engine will process those events the same way every single time. And in our case we record every event as well, so you can take all the events from production, for example, put it on a development PC and either fix bugs or run it again and again to improve performance. Try out different performance approaches. If you move on. Okay, so in this case, the ones in green are queues, and the ones in the boxes in the middle are the functions that are just purely dependent. These are sometimes called lambda functions. More technically, they're kappa functions, which is they are just event-driven systems. And on the outsides, we tend to, like when you're interacting with the outside world and other systems, we have gateways. Their job is just to normalize the data from whatever you're connecting to your internal data model. So they're usually stateless. And so they're usually, once you build a stateless system and all it does is transform, usually becomes quite stable. It only has to change when the protocol changes or your internal data model changes. A lot of the really interesting stuff, the business logic, is in like control systems in the middle. They have to maintain some sort of state in the sense that how they act will depend on previous messages. So, for example, if you want to cancel an order, that will depend on what the order was, right? So that will be a previous event. So the way to still treat this as a function is that it's a function of every event it's ever seen. So every input comes in as an event. Every piece of reference data, every piece of configuration, it gets told absolutely everything. It gets pushed to it, right? And if it does need to go away and get some additional information, it spits out a message in the output that is read by some other system that will pick up that information, then feed it into its input. So now, if you want to test this or reproduce its state for a failover, for a debugging, all you need is the inbound messages in this case and the software for the control system. And you can recreate its state at any point for debugging, for example, and checking you fixed it. You don't need any of the rest. You don't have access to production databases, any kind of production systems. You don't need to run any of the other components because when you're just recreating it, they don't need to be running. That means you've got a nice self-contained testing framework, and it makes it then very easy to develop that microservice in isolation. So one of the key benefits of this approach is it makes it very easy to create regression tests. So a regression test isn't so much saying, for this input, I expect to get that output, which would be nice. That would be the goal. That would be the 100 you got from the business and the 100 you got from IT. But sometimes that detail isn't available to you. So instead, what you can do is create regression tests. So you say, for this input, which I know is a scenario that will happen or might happen, or I need to consider could happen, what does it actually produce? And I can look at what it actually produces, and it's up to me or the team to decide, well, how much do we check that? You can either make it as a pure regression test where you don't even look at it, and then the benefit of that is that if something changes in the future, you will at least know that it changes. You will at least know that it's produced a different output now than it used to do. Which one is correct? You haven't really spent enough time investigating, but you at least know when something changes. Obviously, if you can spend some time saying, does this look sensible? If you can show it to the business and say, does this look sensible? Does this look right? Then that would be great, but that doesn't always happen in reality. But you don't need it to. You can still generate a significant number of regression tests and at least have some stability and be at least aware when things change, perhaps unexpectedly. Because one of the big risks of any change is unintended consequences that you're just not aware of. And this at least will help you cover those. Yeah, so regression tests are very simple. You take a series of inputs, and often you would just take a series of inputs that are valid and have already come up previously, so you don't need to create them from scratch. And then you just play with them. You make invalid inputs, you put duplicates in, you drop out messages that should be there, and just see what the system does. And you can record those results and then check whether that behavior ever changes in the future. And this can be used in realistic cases. So in this case, we've got a series of queues, which are in blue, in between a series of services. So The same queue can go to multiple services. The pricer in this case takes data from multiple inputs. And all of this can be canned and produced into tests and regression tests. And they can be used, the two techniques can be used together. So one of the areas that we differ, and again, I'm still talking about open source products here, is that we advocate using a high-level interface, which is a Java interface with POJOs. That's it. We're not talking about flyweights over off-heap memory or anything really super low level that can be very hard to work with, right? We're talking about being able to still do low latency coding, but still have something that looks like, you know, most Java developers would expect. So these are some sample interfaces. The top one is a really simple one that I use in some of my examples. You've got one event. That one event is modeled as a single method call, which takes one argument, which is a piece of text. In a slightly more realistic example, we've got an input to an OMS, an order management system. You can send in new order singles. You can ask to cancel a request. And in each case, it takes a DTO. And that DTO has all the information associated with it. So the order manager has an input interface, which are all the events that can come in, and has another interface for all the events that can come out. And obviously, you can use things like inheritance and so on to compose these. It doesn't have to all be flat. But going back to the simple example of the say, so you've got it's an asynchronous, it's a bit like asynchronous RPC in that you don't wait for the reply, it's just an event you send. But from a coding point of view, it's really simple. You're making a method call. You don't need to know all the details that, oh, well, actually, this is going to be serialized, and what serialization format am I going to use? And is it going to go to a queue, or is it going to go over TCP? None of that is in the business logic, because that's not what the business logic is about. The business logic is, I have this piece of information in, I need to do something with it, and I need to produce this piece of information out. How you actually do that as a transport or whatever is really a business requirement. Sometimes it is. Sometimes they will know it needs to go over fix, or it has to go to this Kafka queue, or it has to go over here. But often, unless that's a specified requirement, you don't need to be going through all of that in your business logic. So the code to do that is really simple. So there's two key elements to here. The component expects to be given an implementation of where it's going to write out all of the outputs. So it's just an implementation of the interface. In this case, it's the one with one method. And then it has a method which is what gets called when that event comes in. So in this case, because all it does is add an exclamation mark, as you can see, when an event comes in to this component, it will produce the same event going out with an exclamation mark added. And as you can see, this is not low-level coding, right? This is not bytes that you're having to worry about. This is not about off-heap that you're having to worry about, or all of those factors. Because at this point, you're only interested in, well, what is this function supposed to do from the business logic point of view? In reality, all of this can go to off-heap queues and be persisted to disk via memory map files and then over shared memory. But none of those details are important to what you're trying to describe and test at this level. So the way our testing framework works is you have YAML for input and then YAML for the expected output. The benefit of doing that and separating the two is that the output can be maintained very easily. So in the trivial case with a regression test, you don't know what the output should be. You can just generate it, right, from scratch. And in this case, each event is modeled as a document in a field of a document. So that, say, in this case is the field name, but that's the event name, which is the method name. It's just a one-to-one match. And the string that comes after it is the string on the method call. And when you make those method calls in a test harness, it produces exactly the same recorded as an output. Why go through all of this effort? Well, the main benefit is that if you need to maintain this, so I mean, there's lots of different ways you can check whether you got the right result or not. But a lot of the time spent is, if you didn't get the right result, why didn't you get the right result, right? Sometimes in complex examples, that's really hard to find out. And also, sometimes that can be really hard to fix, right? Because I've worked out that this field has changed. I've now got to go into the code, figure out, well, what do I change in this test and now make it pass? And then you have to do this for every test you've got. So say you've got several hundred tests that you have to update. This can be a really, really tedious exercise to go through every test, figure out what's changed, what's wrong, fix what's wrong, and then go on to the next test. Whereas if you use this approach, you could even run it in a mode where it just does a regression test. You run all 600 tests and just overwrites all the expected results. And instead what you do is you review it when you check it in, or you review it as a PR, because and you don't have to even touch the code to do that. That's the ideal case. In reality, it's not always that simple, because you may find actually some of the changes weren't intended, they're not desirable, and you actually have to fix either the test or the code. But let's see what happens if there's a discrepancy. So you're probably familiar with seeing this sort of thing for a unit test failing. It says click here to see the difference, and because it's doing a text comparison, the IDE already has support for this, and it looks like that. So you can see in this case, I changed the input, ran the test again, without changing the expected result. Can anyone spot the discrepancy? As you can see, it's pretty clear. And if I just want to treat it as a regression test, I can now take the actual result, copy paste, overwrite the expected result, and now the test passes. Whether that's a good thing or not is down to your judgment, but you can see that if that is the right thing to do, it's really easy to do, right? And that's even if you're going to go through and do it manually, there's a mode where it will just override it and do it for you. Let's look at a more realistic example where it's more complicated. Because as it gets more and more complicated, that's where the benefit of this approach helps. So this is a new order single from the previous interface. So we've got a DTO now with a number of fields of different types. And one of the things you may notice is that the symbol, which is actually text, so it's an instrument which is something like Eurodollar or IBM shares or whatever, that could be implemented as a string or possibly an enum. But in this case, it's being encoded as a long. And all you have to do is add an annotation that specifies how will I encode it to text and vice versa. You can come up with your own strategies, but base 85 has the nice effect that it uses the 85 most common ASCII characters, and you can get 10 characters packed into a long. So it can be variable length string of up to 10 characters of most of the ASCII characters you're likely to use, and still stick it in a long. If you do that from a text level, that's not going to really make a lot of difference, but from a binary level, it makes a huge difference because this creates no objects, right? It's stored as a long. It also means that comparison is trivial because you're just comparing two longs. You're not having to look into those objects and then compare them. You can also validate them at this point as well. You can ensure if you're in your converter, you can validate whether it's correct or not. That way you won't even import something that's invalid right from the start. Another one that's very useful is encoding the timestamp. So instead of using, say, local date time, which has nanosecond resolution, which is an object, quite a complex object, and quite a bit of overhead, again, you can just use a long, which is the number of nanoseconds since 1970. And in a real example, this is a real test. You can see that in YAML it's still readable as a text. The timestamps appear as a timestamp. The symbol appears as a string, but it's actually encoded for you as a long in binary very efficiently. You can still have strings, you can still have enums if you wish, but you have another option not to use those if for efficiency reasons. So then what happens if I break the test? Is it still easy to see what I broke? Well, you be the judge. Can you see what I broke here? Right? Can you also see if I just wanted to take the expected result and make the test pass, that would be really easy, right? Because without even looking at the code, right? You could fix this without needing to understand, well, if that's the path you're going to take. If you decided actually you shouldn't have done that and you need to fix the code, well, obviously you may have to go into the test or you may have to go into the original code, but in terms of your easy option, it couldn't be much simpler. And we have examples where we've got a megabyte in and a megabyte out of data. And tracing through all of that is really tedious if you break something. But using this technique, it will scroll down to the point and you'll see the exact thing that's different. Now, in a slightly more realistic example, we do add a couple of things to add some functionality. So because we're interested in low latency, and these method names are quite long, from our point of view, it can actually make a difference in a benchmark. You have the option to turn them into numbers instead of being strings. And in fact, we were looking at some numbers today, actually, and the 4 nines, that's the worst 1 in 10,000, can be reduced by a factor of 2 if you use some of the lower level techniques. This is one of them. There are other techniques you can use that in combination can reduce your high percentile latencies significantly. But you don't have to do this up front. This is something you can do later, once you've got the system running, once it's all stable. You can play around with these annotations and see, well, do they help or not? And in fact, even the previous test where I had a string and a date time, that's something you can change later. The YAML doesn't have to change. So once you've built all the tests, they're not touched by this. It's only the implementation you're playing with to optimize it. How are we going for time? I assume we're going good for time, and I'll just go through this quickly. So one of the key things in any project, if you're looking at the end-to-end latency, is there going to be a database in your critical path, and what are the durability guarantees you need? Because if you're going to use a database, that will dominate, and then it will be about, well, how can I use this database most effectively? However, there are other options that can still give you good the durability guarantees, which is, how likely am I to lose data, and how much data might I lose? You can get other options without necessarily going down that road, and that can significantly reduce the latencies involved. And then it does matter how your application runs. So if you started a database, the sort of typical latencies you might see are in the order of 10 to 100 milliseconds. This is often enough in certain applications. However, using other options, you might be looking at 2 to 20 milliseconds, 10 to 100 microseconds, or even 1 to 10 microseconds. And obviously, in our case, we tend to be more at the bottom here. Also, sometimes looking at redundant messaging as well. So in this scenario, the sort of model is that you've got some client or some gateway or some source of information, and you've got a server that's processing that information. What needs to happen before you process it, or before you send a reply? Does it need to go to disk? Does it need to have a redundant copy on another server? Does it need to go to a file so that if the application dies, that's fine? There are a number of different options, and they will make remarkably big difference to how much latency that operation takes. So in the lowest latency option, the least guarantee is, say you've got an application and all you care about is how long will it take to write that message, not how long it will take to process or persist. It's just you've got an application that's being logged or monitored, or for compliance purposes it's being recorded, and you just want to all you care about is the write time. And this is one that's often benchmarked because it's the lowest number you will get, right? Because it's doing the least. But it's something to watch out for, because if that's not your use case, a benchmark that shows you the time to publish isn't going to be very helpful, because that's not what you're looking at. But if all you care about is recording or logging, and that's a very common use case, then the time to publish is the one that really matters. And as you can see, there are options out there, and we're not the only ones, where that delay is extremely small, and this is in microseconds, right? So we're talking about 170 nanoseconds typical latency here. It's extremely low. However, sending the same message, but using acknowledged replication, so you're sending a message to a server and then getting a response back saying that the second server has a copy, that can be still very quick. But we're bringing that up to about 16 microseconds typical, and that'll be either that'll be, I'll say, on a low latency network. So two machines quite close to each other, low latency infrastructure end to end. You can get it down to about 16 microseconds. If you looked at something like AWS, you might be looking at 40 to 60 microseconds, but it's still a very low number. Still much lower than, say, writing to disk, for example. Much lower than writing to a database. In the higher one there is you have the option to give a hint to so you're writing it to a memory map file. You can give a hint to the operating system saying it would be a good idea if you wrote this sometime very soon. So it's not really a guarantee as such, but it is a method call you can take to prioritize, whatever that means to the operating system, writing that data to disk. So it does minimize how long the delay is between writing it and it actually going to disk. And that brings up the uptick a little bit. So what this is doing is it's telling the operating system it should write it out to disk, and it's waiting for at least a copy on a second machine which is close by. And this is actually a pretty good combination. It gives you quite a lot of robustness, but not necessarily as, it's not for all use cases. But you can see that that's actually very low. I mean, we're still under 40 microseconds at this point, and that may not be make a really big difference. Also, it's very consistent, right? So the worst one in 100 is about 72 microseconds. But moving on. What happens if that's not the guarantee that we need, or this is not the guarantee we use? What could be achieved? So the high end here is usually, this is the highest requirement, is that the OS, or at least the hardware controller, not necessarily the disk itself, but the hardware RAID controller, has replied that that data has been written to disk, right? And with spinning disk, that was pretty high and quite bad, but certainly a decent enterprise SSD, which is what is being tested here, you can get that down to about 7 milliseconds, 7,000 microseconds typical, and 99th percentile of about just under 17 milliseconds. And if that's enough for you, then that's the best guarantee you can pretty much get anyway. So that's going to be fine. Now you can add in acknowledged replication, but that's usually so much faster. Adding acknowledged replication won't make much difference. At that point, it's only how long does it take to send a message and get a reply. So it's just down to your network speed at this point. So if your acknowledged replication is from Singapore to Hong Kong, that will be, it's the length, right? It's the speed of light to send a message that fast. That's your bottleneck. Sorry, before you go. What if we can come up with something that's a bit of a best of both worlds here, right? Where, say you're sending a heartbeat, does that really need to be committed to disk? Maybe not. If you're sending a very small trade, so for example, in stocks securities, the size of the trade can vary enormously. So you can have really small trades, and then there'll be a small number of really big trades. And so how do we make it that, well, instead of paying the penalty on every single event, how about we only pay a penalty on the ones that actually have a key risk to the business, the ones the business really cares about and says, these are the ones we can't possibly lose. So what I did here is look at, well, if you took that strategy, and again, it's an assumption because it entirely depends on your use case, what if this only happened 10 times a second? So roughly every 100 milliseconds, a message came in that you couldn't possibly lose, you couldn't continue until it had been committed to disk. But every other message just can go as soon as it's available. So it still means that every message before it has to be committed when this happens, because you need all of them, but you're only doing this periodically. And as you might expect, the typical latency is improved significantly, because typically this doesn't happen. Right? So you get the typical latency, which is similar to just doing acknowledged replication, but then in your higher percentiles, they're going to be dominated by how long it takes to commit to disk. But even they are improved, not hugely, but they're still improved somewhat compared to just persisting absolutely everything. Now, another step you can take is use a faster disk. So this is not a disk this is a high-end, usually used in desktop disk. And there's a number of vendors that do this at the moment. However, in the next couple of years, possibly by the time you have a project that needs this and it goes through, say, a bank or your organization as being an approved disk, they may have these speeds as well, right? So we're talking about where is the market going? And certainly, I mean, this is something you can't buy today, but it may not be an option for you yet. But as you can see, the typical latency is still quite high, but it's down to 1.7 milliseconds at this point, which is pretty good. And there's still a benefit from taking this sort of hybrid approach, where only when there's a trade too big or a message too important or there's too much outstanding data do you actually commit. Yes. So I'll introduce Jerry, who's the local regional MD, and also introduce Vachikan, who is properly local. He actually lives here. So yes, so they can help you out with a bit more detail. I'm based in the UK, even though I'm from Melbourne originally. So are there any
questions? Ping me on that
email.
Yes.
But if you've got any questions you're willing to ask now, go ahead. You can ask me or them. Yes?
So a question about the object allocation.
Yes.
So the bottleneck or the rate of allocation, is it limited by the CPU, the CPU speed, or is it the memory bandwidth or the level 2 caches?
It's more the L3 memory, L3 cache memory bandwidth is the bottleneck. It doesn't seem to, it's not entirely linear with the memory speed either. If you use faster memory, memory that's twice as fast, rated as twice as fast, you don't quite get twice the allocation rate, though. It does help, but that's the limiting factor there. So, so that's why adding more CPUs doesn't really, it does help to a point, but that point at which it helps sort of maxes out at 2, 3, or 4 CPUs. And then after that, adding more CPUs just means they're waiting for each other more for the allocations to go through.
So, level 3 cache?
Yes.
Bandwidth.
Pretty much, yes.
But some of the newer CPUs, right, they are multiple level 3 caches, even within the package?
Yes, so there's core complexes. This one actually had, the CPU I was testing has two, it's an AMD, it has 2 core complexes. So it actually has multiple tiers, and I did test that. There's very little difference between having, say, 16 threads running on the single core complex or 16 threads running across 2 core complexes. It split across 2 core complexes. It didn't really make a lot of difference. So it may be something lower level than the L3, but that's roughly where I would place it as being the bottleneck. Sorry?
Also Google or Amazon.
Yes.
Have you tested this software before?
Well, yeah, if you run in the cloud, you will still run into the same restrictions at the hardware, because fundamentally they all run, for the most part, run AMD or Intel, and they tend to copy each other's architecture in terms of CPUs. So you should get a very, I would expect you get a very similar result. There'll be some saturation point, and it'll be much lower than you might expect in terms of the number of CPUs required to achieve it. Between them. That's the main takeaway. Yeah, I haven't, in our experience, as you add more sockets, you get bigger and bigger machines. Accessing memory generally gets slower, not faster. Like you get more CPU, but your memory bandwidth actually tends to go down because you've got a more complex structure and numerous regions to worry about and so on. In terms of accessing that memory, it actually takes longer. Yes?
Just wondering, like, if you consider, like, Java, for example, like Spring, Hibernate, all those frameworks which use proxies and aspect-oriented programming integrity. Do you consider that maybe in some systems it's not appropriate because they create too many objects?
Yes, certainly in our use case we don't consider them at all because they do create too many objects. However, so often in our core systems we'll try and make very low GC, but then they need to talk to systems that aren't as stringent requirements. So they may create a lot of objects. They may be using Spring Boot, they may be using JBoss for web servicing, they may be using, not all the systems have to be designed this way. But what we tend to advocate, partly for this reason, is that you'll put that on a separate machine, separate physical machine. And then you're kind of isolating the problem to that machine. So then, yeah, it's fine to use all of that, and then you at least won't be impacting the critical path, the critical processes.
And I guess there's garbage when you start up, and there's garbage in the steady state. So we've got lots of customers who use Spring to set up their system, and then after a few minutes after it started, there's no more garbage. There might be some Spring proxies floating around, so you've got to be very careful of them. But if you can avoid them, then you can kick off a GC 30 seconds in or whatever, and you should be running fine.
Yeah. And it doesn't have to be absolutely zero garbage. It just needs to be so low that it doesn't matter. And that might be still surprisingly high in terms of raw numbers. So a common example, and this goes back many years, so I've done this many times, is if you've got a system that's creating, say, a gigabyte an hour of garbage, which if they're 100 byte objects, that's like 10 million objects an hour per JVM, so you can have multiple JVMs doing this as well. But say you can have it under a gigabyte an hour, then that's 24 gig a day, right? So you're still creating objects, still creating some garbage here and there, but it's just not very high level. And then you can start your system up with an Eden space of 24 gig. So you can just watch that Eden slowly fill up over the day. And then you can run, and I've actually done this, do it as a timed maintenance task to do a full GC overnight. So once a day you do one GC, that's it, and then as long as you keep it, say, if you can keep it within the Eden space size, then there are no more collections. This just becomes not an issue anymore. And I tell you, a gigabyte an hour, even going back to my estimate here, you're looking at far less than a 0.1% of the time is chewed up by allocations. Yes?
What would be this sounds like a lot of application for frequency trading.
Yes. Yeah.
80% of the banks is on the air value, user registration or internal backend process. Probably their latency time is one day.
Yeah, that's partly why we emphasize that it's not just about making the applications efficient, it's also about making developers efficient. And often the cost of developers is more than the cost of the hardware, right? And sorry? Yeah, and I mean, the thing is, if you could halve your build time, how much more productive will you and the rest of the team be, for example? Yeah, that's right. And if you could reduce it by a factor of 10, you would probably enjoy your day more, right? For example, you know, it's not just you'd be more productive; it would even be more enjoyable. So, because when you do builds, and you've got an established system, you're actually talking about having to do quite a lot, many times, many variations, quite often, and you would just like all of that to be much quicker. Okay. Thank you very much for listening.